So now let's move on to the next segment. The next segment is about 3D experience simulation. In this particular talk, we are going to present to you how we could use 3D experience platform for concurrent design, as well as doing simulation of complex product assemblies. I would like to welcome on stage Srinivas Thedapalli, Gregor Judex, Carl Kuras, and Sharath Prasad. Take it away, guys.
Thank you.
All right, thank you, Sumant, and good afternoon, everyone. Welcome to General Lecture 2. Today, me and my colleagues, Gregor, Sharath, and Carl, will talk about how the 3D experience platform can help you accelerate with your innovation within your organization. So let's get started here. Let's take a quick recap of what we have seen in the last 1.5 days. We within Dassault Systems believe that there are 3 key ingredients for simulation to power sustainable innovation for product, nature, and life. Yesterday, in General Lecture 1, Bruce and Reza talked about how Dassault Systems is providing the best-in-class technology for our customers. This afternoon, our CEO, Scott Berkey, talked about how the innovator, which is you all, are really pushing the boundaries of simulation. And lastly, the third and the most important ingredient is the platform, the 3D experience platform. And in fact, it's this 3D experience platform that is bringing technology closer to the innovator than ever before. And as described earlier in our CEO Scott Berkey's presentation, it is this platform that is helping us to democratize simulation so that more and more users within your organization can benefit from these great simulation technologies. We have also seen that there are 3 key pillars that are supporting this 3D experience platform, starting with the 3D experience V plus R, which is essentially bringing the virtual and the real worlds together. We have also seen how the data-driven as well as the model-based tools on the platform are really helping our customers. Last year, at the Simulia Community Conference in Berlin, we have demonstrated how this 3D experience platform is helping our customers to move away from just solving a finite element model to being able to innovate and create smarter and better products. We have demonstrated that with the help of a motorcycle workflow, wherein we were showing how a CAE expert or a methods developer can use their own existing tools in an ad hoc fashion and pass this information and IP to the rest of the other team members, where they are able to automate this model development processes, followed by using the concept of templates, where we are capturing these best practices. And lastly, we have also described the technology where you can use all these best practices and deploy within your organization so that the rest of the CAE teams can also benefit from this. This video, by the way, is also available on the Simulia Learning community for your reference. Today, we'll be taking a slightly different approach. We'll be using a business jet example, and we'll talk about some of the challenges different project teams are facing when they need to collaborate with each other and also concurrently work on this large project. If you take a look at this business jet, it's a very complicated structure with multiple levels of hierarchy, starting all the way from the full aircraft structure, which is a very massive assembly, going all the way down to individual materials and coupon testing. And when you're dealing with these types of large assemblies, the challenges that our customers are facing today are being able to manage workloads, being able to synchronize modeling and design schedules, and first, primarily, how do we know who is working on what? So some of the challenges are essentially managing in the context of these large multi-level assemblies, where the scales are changing from full aircraft structure all the way to a single component. Imagine there is a design change at one of these levels in this hierarchy. We have to ensure that this design change is propagated throughout the rest of the hierarchies. So some of the challenges here in this context are managing design and simulation changes so that the design team and the CAE or the simulation teams are always synchronized and working collaboratively. Oftentimes, it's not just the structural analysis that's performed on a large business jet model like this. There are requirements coming from different disciplines. And in this particular case, let's assume we are looking at a passenger comfort. So here, the challenge is being able to manage requirements coming from different disciplines in the context of multi-physics modeling. And lastly, on a large business jet program like this, thousands of tests needs to be performed. So the challenge here is, how do we make sure that we are always comparing the right set of results that are coming from the virtual and the real worlds? So if we were to summarize, these are the 4 specific challenges that we'll be talking about, and we'll demonstrate with specific examples how the 3D experience platform can alleviate with these types of challenges and projects which are being worked on concurrently at the same time on the exact same digital mockup. So I'll be talking about managing the multi-level assemblies. My colleagues Gregor will then describe and demonstrate how we can manage design and simulation changes. Sharath will then talk about managing the multidisciplinary requirements. And lastly, Carl will then demonstrate how we can bring this virtual and the real worlds together. So let's get started here. As a meshing and modeling team lead, the first thing that I can do here is take a look at my dashboard on this 3D experience platform. A dashboard is essentially a web-based application that gives me all the critical information that I need for this particular project in one single snapshot. I can search and filter all the data that I'm interested in. I can also take a look at all the tasks that have been assigned to me as well as my team members. In this particular case, the 4 specific tasks were create a global finite element model, detail nonlinear finite element models for the wing box, fuselage, and the landing gear, as well as creating multiple representations at the component level. I can also use this 3D Play application within the dashboard, which I will be using. So what you're seeing here is the data that me and the rest of my project team members will be using for this project. So in this specific context of managing these large multi-level assemblies, I'll demonstrate 2 specific technologies. The first one is automated modeling, followed by multi-level collaborative modeling. So let's get started here. The first thing that I do is start to create mesh rules. A mesh rule essentially gives me the ability to capture all the best practices and requirements based on my IP. In this particular case, I can create a mesh rule to create a very high quality shell mesh. For example, if you take a look at this, a mesh rule essentially helps me to capture my global element size, local element size, any geometric cleanup if required, as well as capturing specific geometric details such as holes, fillets, beads. Similarly, I can create another mesh rule to create a very high quality hexahedral mesh or even a continuum shell mesh. And there's really no limitation on the number of mesh rules I can create. It can either be a combination of shells, tetrahedrals, as well as hexahedral elements. Once I have these mesh rules created and then saved on the 3D experience platform, the next thing I do is launch the automated modeling tool. Automated Modeler is a very nice capability that is available on the platform, which will help users create large meshes in a very short span of time. In this particular case, all the individual parts of the landing gear assembly are listed here, and the wing box. I can use filtering tools to quickly filter some of the parts that I am interested in this particular case, all the ribs, as shown here. The next step I do is apply a user procedure. A user procedure is a new technology that's available on the platform that will help me create geometric abstractions, such as mid-surface extraction, automatically in the context of such a large assembly. The next step I do is then apply the mesh rules that we have already created and saved ahead of time. I can quickly search for a mesh rule that either myself or some of my team members have created. Thanks to the collaborative nature, users can quickly search and apply these mesh rules. It takes a few minutes for me to apply different mesh rules for this complete wing box and the landing gear assembly, which is a combination of hexahedral elements, tetrahedral elements, as well as shell elements. I also have the ability to perform this meshing either locally or on a remote HPC cluster. In this particular case, when I submit this on a remote machine, I have the ability to use the power of distributed computing, meaning I can use more number of cores to create a very high quality mesh in a very short span of time. So now, when I run this automated modeler, as can be seen here, the user procedures were able to extract the mid-surfaces for all these thin parts, and it were also able to apply the thickness from the underlying solid. It creates a very high quality shell mesh, tetrahedral mesh, as well as a continuum shell mesh, depending on the mesh rules that I have used in my automated modeler. We have performed the exact same process as described earlier on a separate set of subassembly. What you're seeing here is a section of the fuselage. If you deep dive and take a closer look at it, again, the mid surfaces were automatically extracted, and the thickness was also applied from the underlying solids. I am now going to isolate one single component of this particular subassembly. And then, if you zoom in, you will notice I can quickly turn off the geometry and just only show the resulting shell mesh that was created with the help of the rules-based mesh as well as the user procedure. We now also have the ability to map the thickness automatically from the underlying solid. What you're seeing here is the thickness that was automatically computed and then applied to this resulting shell mesh. This particular difference in the color indicates that it was a variable thickness in that particular location. And our mesher was precisely able to extract the thickness and then apply it appropriately for those set of nodes or elements. And this is just a close-up view of that particular part. This is all great, but it is oftentimes the users, which are you all, which are really pushing the boundaries of simulation. When you're looking at a very large business jet program like this, it's not just dealing with small parts and assemblies, but these are massive assemblies where the sizes are ranging from full aircraft to a single component. And some of the challenges that our customers are facing when dealing with these types of massive assemblies are, firstly, how do you know who is working on what? How do you synchronize your design and simulation schedules? And how do you manage all your workloads? 3DEXPERIENCE platform and the applications available on the platform deliver some very nice capabilities to quickly take a look at this. For example, if you take a look at all these individual subassemblies on the turntable, I can use the business intelligence tools that are available out of the box and quickly query some of the statistics, such as which team is working on a particular subassembly. A green color here indicates that I have logged that particular assembly and started working on it. A red color indicates my other team members have also started simultaneously working on the exact same business jet. Now, in this particular case, we have applied the exact same rules-based meshing and the automated modeling techniques as described earlier and created a global finite element model, which will be used to compute the internal loads. One of the unique capabilities we have here is, without compromising the original digital mockup or the CAD product structure, we now have the ability to create multiple representations, starting all the way from a full aircraft structure and going down the hierarchy as described earlier. In this particular case, this was the exact mesh that I showed you, which was created on a section of the fuselage. Again, the important thing here, we did not disassociate the CAD product structure to the simulation model. The platform also gives me the ability to create multiple representations, either at a single component level or even at an assembly level. In this case, I can either create a shell mesh or a solid mesh, which can then be used for the structural integrity testing. So in summary, what you have seen in the past few minutes, especially in the context of meshing and managing these large multi-level assemblies are, firstly, we have demonstrated the concept of rules-based meshing. We have also showcased the automated modeling in conjunction with the user procedures, which can be used to automatically extract the mid-surfaces for large assemblies in one shot. We've also demonstrated how the 3DEXPERIENCE platform can automatically extract the thickness from the underlying solid and then apply it to the resulting mesh. And lastly, we have demonstrated some of the capabilities that we have on the 3DEXPERIENCE platform that will help our customers simultaneously work on the exact same digital mockup based on different requirements that are coming from the different product development teams without compromising the original CAD product structure. While me and my team members were simultaneously working on creating these beautiful meshes for downflow applications, my colleague Gregor and his team members, they started to create fasteners to put all these meshes together. And now he's going to demonstrate how he is managing design and simulation changes concurrently while we were working on creating these large meshes. It's up to you.
Thank you. Thank you, Srinivas. Let me first come back to the pyramid of our business jet program that Srinivas introduced at the beginning of our presentation. And as he explained, it illustrates different levels of detail. And by that, and moreover, it stands for multiple groups working together on a common project. And the red circles indicate that updates have to be performed between the various groups. And by that, the red circles also indicate one of the main challenges we're facing today, which is to account for design and simulation changes. Now just think about how often you had to rebuild your CAE model, your analysis model, because the design has changed. Today, this mostly is a manual process, which is tedious. The exchange between the various tools is file-based, and the whole process disconnected. But what we are really looking for is an automatic update procedure, a data-driven approach where everybody can rely on the same data, on the same data model, and can retrieve the most and latest recent information at any point in time. And you may also look for an integrated process management that can help you organize the tasks of your team. So these are the values I want to demonstrate within my section. And for that, I want to use a fastener workflow. Simply because this is a quite complex workflow. Several people and multiple teams are involved, and design changes are very likely to occur. So let me explain this workflow briefly. There are the design engineers who are creating the geometry. Then we have the manufacturing engineer who is responsible to create the connections and the fasteners. And then there's the mechanical analysts. And I guess most of you are mechanical analysts. So we utilize the geometry and the fastener information to create our Abaqus finite element model and run the analysis. So one outcome of that analysis could be that a design change has to be performed. And we run into a design cycle. Now, since all my engineers are working on the 3DEXPERIENCE platform, this design change can be accounted for very easily and quickly, because we all rely on the same data, and we rely on a single source of truth, and everybody can update his model with reading the most recent information from the 3DEXPERIENCE platform. But before I want to go into the detail of this design change, let me elaborate a little bit on the role of the manufacturing engineer. So he's responsible to create the fasteners, and for creating the locations, there are several different options available, including the most common one of using existing geometric points. Then a huge advantage of our solution is that the connecting surfaces are found automatically, so that you can create hundreds of spot welds within one shot. And the stacking menu lets you then verify and edit these connections. And additionally, you could also store any kind of manufacturing information together with every single fastener so that it can be used in any downstream process. Now let's review how this looks like within the product. So we start the fastener application here and the instantiation process. We select the geometric points, and then within the stacking menu, we can verify the stacking and edit it. And then when we're done with that, the fasteners are created, and they are shown as yellow cylinders within the product. So now those fasteners can be used in the downstream process. So the mechanical analyst can import them into his finite element model. Other options include reading the fastener information from a text file that holds the coordinates of the locations. Then for the connection to the mesh, you can pick and choose between a kinematic and a distributed coupling. And then we provide several options regarding the element type, which I want to go in more detail on the next slide. So firstly, there's line elements, which could be a spring, a beam, or a connector element, also including a rigid connector, if you like. Then many of our customers prefer to use hex elements, which are also supported. And then we also provide an assembled construct that consists of multiple connector elements that define the tension and the shear behavior of the fastener, and you could also include pre-tensioning. And this assembled connector can be used for not only regular shells, but also continuum shells and solids. Now, the mechanical analyst can import the fasteners directly from the 3DEXPERIENCE database. He can select which kind of coupling and which kind of element type he wants to use. And then when I zoom in into those regions where the fasteners have been created, you will see that the couplings have also automatically been created to connect the fasteners to the existing mesh. So with that, we ran through the process once. We've created the fasteners, and we've created our analysis model. Now let's come back to the change scenario. So as I said, since all my engineers are working on the 3DEXPERIENCE platform, this change can be accounted for very easily and quickly, because we all rely on the single source of truth. Now, for managing this change, imagine I'm the project manager. And as a project manager, I'm working with all those teams from the different departments. And to manage these tasks, I prefer to use a route of tasks, which means in a route of tasks, the tasks are defined in a predefined order. And when one task is completed, the next one gets automatically assigned to the next person. So as a project manager within my web interface, I can organize the projects and the tasks of my team. And in this specific scenario, I'm starting the route for the change scenario. And by that, the first task gets assigned to David, who is our design engineer. So when David now logs into the platform, he will see that a new task has been assigned to him, and he will start his work from here. The task will include everything he needs, all the information he needs. In this specific scenario, we have a 3D review which tells him that the stiffeners have to move from the red to the blue positions. Now he can directly start from here by running and launching the assembly app. And we have stored the new positions of the geometry in a new revision. So when we check the revision status in our product, we will see all parts in red for which a new revision exists. And now we can simply load the latest revision to our product, and by that the stiffness moves to the new position. When we zoom in, we will see that the fasteners are still out of date, and we will work on those just in a moment. Now back in the web interface, David can approve his task as being finished. And by that, the next task gets automatically assigned to the manufacturer engineer. So Mike, the manufacturing engineer, can now work on the fasteners. He can verify them and he can edit them. In our particular case, the only thing the manufacturing engineer has to do is run the automatic update. And this is really one of the huge benefits of the 3DEXPERIENCE platform, because again, we all rely on the single source of truth. And he can retrieve the most recent data for these fasteners and apply for these changes with the automatic update at any point in time. So now with that, the last task gets assigned to Sam, our mechanical analyst. Now, when we zoom in into Sam's model, we will see the couplings still reside in the old position. But when we re-import the fastener informations and run the update, then they get recreated at the new positions, and the couplings get recreated to be connected to the mesh again. So with that, we ran through the whole change scenario. The analysis model, the Abaqus analysis model, is ready to be rerun, and our route is completed successfully, and the project manager gets informed accordingly. And what have been the highlights I've shown you? Firstly, there was project management, which can help you organize the tasks of your team. Then a huge benefit of the platform is that it provides a single source of truth. With its data-driven approach, where everybody can retrieve the most recent data at any point in time. And then the automatic update procedure can help you in any change scenario. So far I've shown you how to handle design and simulation changes on the 3D Experience platform. And with that, I want to introduce my colleague Sharat, who has simultaneously been working on the multiphysics project. And he will show us how he is managing multidisciplinary requirements in the context of this Business Jet program. Sharat?
Thank you, Gregor. I am the team lead for the multiphysics design team. My team is responsible for design and simulation activities from a multiphysics and multidisciplinary perspective. In order to keep track of the activities of my team, me and my colleagues use the 3D dashboard. For the Business Jet project, all of the tasks that we need to perform, they have been listed right there. We need to take care of two specific tasks for the Business Jet project. The first task is to simulate the airflow inside the cabin. We want to evaluate the temperatures and velocities experienced by the passengers in order to assess their comfort level. This task needs to be carried out for different cabin configurations. These cabin configurations could include different seating arrangements, as well as different HVAC inlet and outlet vent placements. The second task that my team needs to take care of is to assess the risk of pathogen transport within the cabin. Simulating the airflow inside the cabin requires a CFD analysis. A typical workflow starts with the CAD for the cabin. We then extract the fluid computational volume on which the CFD computations will be run. The fluid computational volume in this case is the interior of the cabin, which, by the way, is not available to us. Once the fluid computational volume is available, we will set up a boundary layer mesh in order to capture the accurate physics of the turbulent flow. Once this task is done, we create the CFD physics as well as the boundary conditions. This task is very important because this is what brings the problem from the real world into our virtual world. We then run our simulation. We have all of the results that we need. These results can give us a good insight into the cabin airflow. Now, if you are familiar with this workflow, historically, this workflow is a very long, very manual, and a tedious workflow. A significant amount of time is spent in moving from CAD to extracting the fluid computational volume to essentially setting the boundary layer mesh. We also need to carry out this workflow for not one, but for many different cabin configurations. These different cabin configurations could include different seating arrangements of rows, as well as different HVAC inlet and outlet vent placements. Now imagine carrying out this workflow for different cabin configurations entirely manually. The task would be very manual, very repetitive, and quite laborious, and it would also be prone to error. 3D Experience platform provides us very strong and powerful set of tools to avoid a lot of these repetitions. CFD technology, tightly integrated with CAD and the product structure, is one such tool that I'm going to demonstrate now. So we start with the CAD for the cabin. We use the fluid domain tool. We select all of the parts and assemblies that form my fluid volume. We also select a surface and a direction in order to specify that the fluid computational volume in this case is the interior of the cabin. Once done, I switch to meshing, and I use the hex dominant meshing tool to specify a boundary layer mesh with minimum and maximum mesh sizes. We then simply update the mesh, and in a few minutes, I have my first mesh in my hand to review. We use cut planes to review the interior of the domain. As you can see, the interior of the cabin has automatically been calculated, and a nice boundary layer mesh has been set up. Now, let's assume that you want to change the cabin configuration by increasing the number of rows of seats from 4 to 5. It's very easy. You simply access the product structure. You have a number of parameters available that control not only the number of seats, but other things such as the number of inlet and outlet vents, as well as their sizes and placements. We update the number of seats, go back to meshing, and simply update the mesh. In a few minutes, I have my new mesh in my hand. As you can see, the cabin configuration has been updated, the number of rows of seats have been increased to 5, and a new boundary layer mesh has been automatically created. Now, one of the things that I have not demonstrated here is that the CFD attributes like boundary conditions and CFD physics and other things that you create, they are also automatically updated as well. Another strong and powerful tool that 3DEXPERIENCE provides us is the ability to use CFD simulations within a simulation process. Here you can see that I am using CFD simulation within a simulation process that has been developed to automate the cabin thermal comfort simulation experience. Another nice thing is that these simulation processes can be deployed as a simulation experience with a very simple-to-use user interface in a web browser. The key benefit here is that now non-experts can come in. They can set different parameters associated with number of rows, for example, parameters associated with HVAC configuration and cabin conditions, and quickly run simulations. Once they run the simulations, they will have all their results in their hand. They can analyze the temperature on the surface of the mannequins, which is the representation of passenger in this case. They can also visualize the flow patterns inside the cabin. They can see how the air is flowing. In this case, they can see the flow streamlines, and which have been colored by temperature in this case. As you can see, the air is coming out of the inlet vents, heading to the outlet vents, with some amount of air that is not being refreshed. You can also review the air velocities on cut planes inside the cabin. This gives a quick idea of the air jet impingement effect on the passengers. The second task that my team needs to take care of is to assess the risk of pathogen transport within the cabin. Now, in case you are wondering what this is about, remember your plane ride into Boston a few days back. How did you feel when somebody kept sneezing or coughing in your back seat? Were you concerned that you could possibly catch a cold? Well, a CFD expert can give you your answer. The expert can model a sneeze or a cough with a velocity boundary condition and specify a pathogen concentration. The expert can then run a transient CFD simulation with species transport. Once the simulation is run, results are in your hand, and you can visualize the flow of pathogens within the cabin. If you visualize the flow of pathogens within the cabin in this case, you can see that when the guy sneezes, actually the sneeze is able to reach to the passenger in the front row. However, it's not spreading to the rest of the cabin. It would have been nice, perhaps, if the person would have covered his face with a mask or with his hands. Now, 3DEXPERIENCE provides us the CFD technology, which is tightly integrated with CAD and the product structure. So you could quickly go back, change the HVAC inlet and outlet vent placements, and investigate all of the different alternatives that could possibly improve the efficacy of removal of pathogens from within the cabin. Let me quickly summarize what I talked about in last several minutes. We saw how we can use the fluid domain tool to automatically specify the fluid computational volumes. We saw the hex-dominant meshing tool that sets up a boundary layer mesh in a rather straightforward fashion. We also, what this enables us to do is to run CFD simulations that are very tightly integrated with the CAD and the product structure. You could quickly change your CAD, you could quickly set your parameters, and you can run many, many different CFD simulations. We also saw Abacus CFD Solver on the 3D Experience platform that can model laminar as well as turbulent flows in both steady state and transient time domains. We saw multi-species transport functionality, modeling the transport of pathogens within the cabin. We also saw that we can capture multidisciplinary requirements on 3D Experience platform, with CFD being one of the core technologies being available to us. While me and my team has been working on capturing the multidisciplinary requirements, my colleague Carl and his team has been working to bring the virtual and real together on the 3D Experience platform. In order to learn more about it, I would like to invite Carl to the stage now.
Thank you, Sharat. Hello, everyone. My name's Carl, and for my tasks, I'm going to use the 3D Experience platform to connect the real and the virtual worlds. Performance testing of the business jet will rely both heavily on virtual tests and simulations and physical tests. And in many cases, these test data and virtual test data will be codependent. We may extract forces from a physical test and apply those to our simulation models, or material data and behaviors from physical tests to our virtual simulations. And at the end of the simulation process, we might want to validate our simulations with physical test information. In order to manage the interactions between physical test data and simulation data, we need an environment which allows these data sets to coexist, but also to provide us with essential links between those data sets to make sure that we are accurately capturing and matching a physical test data set to its virtual twin. So for our example of the business jet, I'm going to use the business jet to validate a set of simulation results. And this will spawn a couple of tasks for me. The first will be to define some strain gauge locations on my business jet to pass this to the physical test team. And the second will be to spawn a submodel simulation to get some local, accurate simulation results, very localized around the region of interest, in this case around the window frame. My final task will then be to take the simulation results and the physical strain gauge signals and compare those data using the tools on the 3D Experience platform. The key challenge in this task is being able to accurately match the physical test data to the virtual tests to make sure I'm extracting the right load case, to make sure I'm working on the right aircraft program. There may be hundreds of tests we perform during the life of a project, and I need to make sure I'm comparing the right physical test data set to its virtual twin. So as with my colleagues, my tasks begin with the dashboard, and I can see the 3D model that I'm working on at this current time. And on the left-hand side here, I can see all of the tasks that are assigned to my team. My first task is to review a global set of simulation results, and from this review, I can then evaluate where to position strain gauges for the physical test, and I can trigger my submodel simulation. And finally, I can compare the results of those two. Linking through to my first task, I can see that I have some attachments that I can already link to. In this case, directly linked to the simulation results of my global model. This allows me then to interrogate the simulation data for my global simulation, to review the areas where I might want to trigger a submodel for further investigation, and also to position the strain gauges required to validate those simulation results. Once I've made that evaluation, the deliverable for this task can then be attached to the task, which in this case is a design review. Again, I've attached my deliverable, which is a design review. I can open that to show you within the 3D Experience platform, and here we can see the engineering decisions that are captured and stored with the 3D model. So here I've highlighted the submodel region that I want to trigger and the locations of my strain gauge arrays that I want to define as part of my further study. And all of this information is then stored on the 3D Experience platform with my 3D model for my colleagues and myself to reference in the future to record that engineering decision. For the remaining tasks, I'm going to use some deployed processes that have been defined for me that will allow me to capture key workflows that we use regularly. At the start of this session, Scott talked about democratization of simulation, and within the 3D Experience platform, we can capture end-to-end processes and all of the activities to define a complete process, capture each of those required steps, and manage all of the data on the platform. As an example, I show here the end-to-end process for an Abaqus submodel captured using the tools. A user running this process will be prompted first to select the global geometry for their study. The process will then export that geometry to the user's desktop for further work. The next activity will be to create the Abaqus global model and manage the data defined by that global model, the global results. And the final activity will be to create and manage the submodel simulation and store those results on the 3D Experience platform. So we've captured the entire process within the 3D Experience platform. During the life of the project, I may run a number of different processes, and you can see the list here. I have several already run and accessible. Fortunately, the 3D Experience platform provides some really powerful tools to filter those simulation processes by who created it, when it was created, which project it's associated with, and so on, so we can trace exactly the process we're looking for. But in addition, when I run these processes, I can attach some specific simulation attributes, such as the aircraft program I'm currently working on. Maybe I want to store the load case information that I'm working on, and the submodel level in this case. And again, the 6W tags allow me to filter based on these custom attributes so that I can very easily and robustly find a specific simulation process relevant to the work I'm doing. So let me perform the first task. I'm going to create the strain gauges for physical testing. I start from the same interface, and I can define the attributes associated with this test, the aircraft program, and the load case we're working on, and submit that task. This will open CATIA directly on the 3D Experience platform, and I can then use some custom tools which will allow me to define the strain gauge location directly on the 3D model. Here I can use some engineering templates which will allow me to position, based on a library, the strain gauges required for my physical test. I position them directly on the 3D model. I can then store that location and the strain gauge orientations directly with my 3D model. Once I've completely defined the strain gauge array, I can then record that and create a report that stores all of the strain gauge locations, all of the strain gauge types, and all of the orientations, and I can pass that information to the physical test team in order to position the strain gauges on the test rig. My next task is to create the submodel within the 3D Experience platform. And again, I use a process to do this, and I can assign the same attributes, the same load case information, and the same aircraft program, and this time I'm launching Abaqus CAE. The reason I'm using Abaqus CAE in this case is over a number of years we've developed plugins, and I'm sure many of you have developed your own plugins to work with Abaqus tools and many other tools, and we can continue to leverage this key investment, which in this case is a submodel script which will rapidly create robust submodels within the CAE environment. So we can still leverage the power of the 3D Experience platform to give us the traceability of the models, but while using your tools and investments that you've made in plugins and so on. Once the process is run, I can then review the submodel results directly within the 3D Experience platform in the context of the global model. My final task is to then compare the physical strain gauge results with the virtual results. And again, I can use processes deployed processes to trigger those tasks, and now that I have these simulation attributes to match the load case and to match the aircraft program, I can make sure that I'm comparing the right physical data with the right simulation data. In this case, I can use the dashboard to present that simulation data and the physical test data within the same view. And I can take that plot, take my physical test data plot, and drag and drop that onto my strain gauge data from the virtual test to perform a more detailed comparison of those. A nice feature of the dashboard is that I can then configure a complete dashboard report to show my entire strain gauge array. Here, each row is representing a single strain gauge from my physical test and virtual test, and finally, on the right-hand side, the complete comparison between those results. And I can then share these dashboard reports with my colleagues across the enterprise. So what are some of the highlights that I've shown over the last few minutes? Well, the first is that I've shown how we can launch and manage both native applications, such as CATIA and our Simulia modeling tools and simulation tools, and external tools on the 3DEXPERIENCE platform and manage those procedures. I've shown how we can assign attributes when we run those procedures to provide vital traceability to enable us to link the physical data with the virtual data. And I've shown how we can then use the 3DEXPERIENCE platform to manage those data sets effectively and make those right comparisons. Okay, so I'm going to close the session and this lecture now just by circling back and talking about the key role of this general lecture, which was to accelerate innovation. And we accelerate innovation, or we've shown how to do that, by really tackling some of the key challenges that our customers face. In General Lecture 1, we were told and explained it in detail the benefits of linking multiple levels of simulation. And so we need to be able to provide an environment to manage multi-level assemblies. We also need to be able to perform very rapidly different designs to be able to achieve the best design. So we need to be able to react in an agile way to design changes and simulation changes. We need to extend our requirements for simulation beyond just structural validation and into passenger comfort and various different other requirements for a business jet. And we need to combine and leverage information from both the virtual and real data sets in order to improve our simulation processes. We achieve this using the 3DEXPERIENCE platform. So Srinivas showed us how we can rapidly generate and manage different levels of finite element model, all within the same data set. Gregor showed how our data-driven environment allows us to very quickly identify changes and react to those in an agile way so that we can perform many more simulations on many different designs and achieve a better design through this. With his passenger comfort example, Sharat showed how we can now account for multi-physics on the 3DEXPERIENCE platform, provide different data models and different simulation models to enable us to account more way beyond structural simulation into passenger comfort requirements. And I have shown how we can combine both the virtual and real test data on the 3DEXPERIENCE platform. With that, I'd like to thank you for your attention, and I'm sure if you have any questions or if you would like to have a practice and play with the 3DEXPERIENCE platform, I would invite you to our early bird session, which starts at 7:30 tomorrow morning in Orleans room, which is just across the way on this floor. So thank you very much for your attention.